In this lesson, we explore the topic of carbocation rearrangements. This is traditionally a topic that is quite challenging for organic chemistry students, but what I'm going to do is look at one specific example and try to really break it down step by step. So if you understand how this type of rearrangement works, you can then generalize and understand the principles of how rearrangements work in general. So as we have seen in looking at the dehydration of a secondary alcohol, secondary carbocations can exist under forcing conditions, but they are still unstable. If they can do anything to increase their stability, they will. So through a carbocation rearrangement, a secondary carbocation can become a more stable tertiary carbocation. So let's see how this works. The simplest case is when a secondary carbocation is adjacent to a quaternary carbon. A quaternary carbon is simply defined as a carbon bound to 4 other carbons. So drawn here is the secondary carbocation that's an intermediate in the mechanism of dehydration of 3,3-dimethyl-2-butanol, the example that we looked at in the previous lesson. So note that the positive charge is on the secondary carbon, on carbon 2, but then on carbon 3, there are 3 other methyl groups bound to carbon 3. So carbon 3 is an example of what we call a quaternary carbon. So what's going to happen? Well, the methyl group is going to migrate with its electrons from the carbon-carbon bond, the methyl group that I have indicated in blue here, from carbon 3 to carbon 2. Okay, so remember, it's moving with its electrons. So the source of the electrons, the tail of the arrow, is the carbon-carbon bond. The destination of the electrons, the head of the arrow, is the cationic carbon. So moving these electrons over to the cationic carbon takes care of the positive charge problem on carbon 2. But because those electrons are moving away from carbon 3, now carbon 3 has to take on the positive charge. But this is an advantageous situation for the ion because it was previously a secondary carbocation and now it is a more stable tertiary carbocation. So when you have this quaternary center, even if you move one methyl group with its electrons, you will still have a tertiary carbon to put the positive charge onto. So having seen this principle, let's finish the dehydration mechanism of 3,3-dimethyl-2-butanol that we began in the previous lesson. So what I just drew is step 3, rearrangement of the secondary carbocation to give the more stable tertiary carbocation. And now what we need to finish the mechanism is removal of the beta hydrogen to give the alkene. Okay, so remember, this is a dehydration reaction, so water has to be the base. We have an arrow going from the lone pair on oxygen to the beta hydrogen that's getting removed, and then another arrow from the carbon-hydrogen bond to form the carbon-carbon bond between carbon 3 and carbon 2. And note that I have only shown here the pathway leading to the major product, which is the Zaitsev product, the more substituted alkene. Want to go over one more example of a carbocation rearrangement. This is kind of a neat one, and it's what we call a ring expansion rearrangement. So methyl groups are not the only groups that can migrate in a rearrangement. So an interesting example is when a rearrangement can relieve angle strain in addition to forming a tertiary carbocation from a secondary. So consider dehydration of the following alcohol. This looks a little similar to where we started with, except now we have a 4-membered ring. So when you see a 4-membered ring, the first light bulb that should go off in your head is angle strain. The second light bulb should be torsional strain, but that's actually not relevant to this problem. What's relevant to this problem is the angle strain. And if there is some way in the course of a mechanism involving this structure to relieve that angle strain, the structure will find a way to do that. So let's look at this. If you treat it with phosphoric acid under dehydration conditions, the first two steps of the dehydration mechanism leading up to the secondary carbocation are exactly the same as the steps we've seen in our previous dehydration mechanisms. You protonate the alcohol with the hydrogen from phosphoric acid to turn it into a good leaving group. This is a proton transfer reaction that requires two curved arrows. And then the leaving group water leaves to generate a secondary carbocation. Next, we have the rearrangement step. But in this case, instead of the methyl group migrating in the rearrangement step, a side of the ring migrates. And what I have done here is I've numbered the carbons to make it easy for you to see what's going on. So I arbitrarily started with carbon 1 at the end of the longest chain. So the cation is at carbon 2, and before rearrangement, the four-membered ring is carbons 3, 4, 5, and 6 with a methyl group on carbon 3. So it is the side of the ring, the bond between carbon 3 and carbon 6 that moves. Those electrons jump from carbon 3 to carbon 2. So now in the post-rearrangement cation, which is now tertiary, carbon 6 is bound to carbon 2, and there is a positive charge on carbon 3. Note there is still a hydrogen atom on carbon 2. That hydrogen atom has not moved. That is, in fact, now the beta hydrogen that gets removed in order to take us to the Zaitsev product. So once more, the base is water, which is a small base. It removes the hydrogen on carbon 2, and then the electrons from the carbon-hydrogen bond go and form the double bond between carbon 2 and carbon 3, giving us the tetrasubstituted alkene. Okay, so carbocation rearrangements are one extra step that gets added to certain mechanisms. They happen under cases in which a secondary carbocation can rearrange into a more stable tertiary carbocation. And then we also saw an interesting example of how, in addition to making a tertiary carbocation, you can also relieve ring strain through a carbocation rearrangement. So rearrangements tend to happen in carbocation mechanisms when there is some gain to be had through carrying out the rearrangement. This generally complicates mechanisms that go through carbocations and makes them less useful if you want to get one product in a high yield. Because while I have shown the pathway leading to rearrangement, it is also possible in some cases to have a pathway that does not involve rearrangement. Furthermore, I only introduced you to one kind of rearrangement, the shift of an alkyl group. There are other kinds of rearrangements, such as the shift of a hydride or what's known as a pinnacle rearrangement, that also can complicate product mixtures under mechanisms that go through carbocations. But for the purpose of this introduction, as I said, I just wanted to focus on a single rearrangement mechanism. Drawing the arrows for it is not difficult. The arrows make perfect sense based on your understanding of how arrows function. They go from the source of the electrons to their destination. The electrons move one carbon, and the positive charge moves one carbon in the other direction.